Hi all. Lastly, we have discussed linear combination of vectors. For example, uh, if v1, v2, etc. are uh, the vectors of these are elements of a vector space V, is a subset of V, then linear combination of these vectors is defined as d1 times v1 plus etc. plus dn times vn. If u is equal to this, you can say that this u is a linear combination of vectors v1, v2, etc. vn. This is the definition of a linear combination. Okay. For example, we consider two elements 1, 0, 0 and 0, 1, 0 in R3. R3 is a vector space over R. Then we need to verify that a vector 1, 1, 1 is a linear combination of these two. Okay, otherwise we will verify that this is an element of set of four linear combination of this. Okay, so in order to get this is a linear combination of these two vectors, we need to assume that d1 there should exist d1 and d2 such that d1 times 1 0 0 plus d2 times 0 1 0. Okay, if this is in the linear combination of vectors, these two, we can say that there exists such d1 d2. If there is no such d1 d2, we can say that this is not in the linear combination of this collection, or 1 1 1 is not a linear combination. Okay, so assume that this is a linear combination of these two vectors. Then we can write this 1 1 1 is equal to by multiplying with this d1, you can get the vector d1 0 0 plus this is d2 sorry, this is 0 d2 0 d2 0. When you multiply d2 with this, you can get this one. So this is equal to, by adding component wise, you can get d1 d2 0. This implies that d1 is equal to 1 and d2 is equal to 1. Okay, but d1 is equal to 1, d2 equal to 1, we can get when you substitute this in this one, you can get 1 1 1 equal to 1 times 1 0 0 plus again d2 is 1 1 times 1 0 1 0. But this is a contradiction, because when you add these two vectors, you can get 1 1 0. The last component is always 0 if we add these two vectors. So we can say that this is not equal to this one. So there is no d1 and d2 which is satisfied by this equation. Okay, so we can say that this 1 1 1 is not a, so this is the conclusion, 1 1 1 is not a linear combination of the vectors 1 0 0 and 0 1 0. Yeah, this is the meaning of linear combination. Now a set of all linear combination of the vectors, combination of a set of vectors say S equal to v1 v2 etc vn is called span. Okay, it's called the span of the vectors v1 v2 etc vn, or simply you can write span of S. Okay, so set of all linear combination of the vectors v1 v2 etc vn is called the span of v1 v2 vn, or span of S, and this set is denoted by set of all d1 v1 plus etc plus dn vn such that di belongs to R, or corresponding field. If you consider a vector space, then if you consider a vector space right, let V be a vector space over F, then the set of all linear combinations of a set of vectors v1, v2, vn, which is subset of v, is called the span of v1, v2, vn, or the span of S, that is denoted by this set. For example, we write or we consider the vector space V as R4. R4 is a vector space over R. Okay, R4, and consider V1 is equal to the vector 1, 0, 0, 0, and V2 is another vector in R4 which is equal to 0, 1, 0, 0. Okay, now we can define S is equal to V1, V2 consisting of two vectors, then consequently span of S. What is span of S? The span of S is set of all D1 times 1, 0, 0, 0 plus D2 times 0, 1, 0, 0 such that D1 comma D2 belongs to the corresponding field. Here the field is R. Okay, since we are constructing R4, R4 is a vector space over R. Now this set becomes set of all. When you multiply this with this vector, the first vector will be D1 0 0 0 plus D2 0 D2 0 D2 0 0. Okay, such that D1 comma D2 belongs to R. Okay, so this is equal to set of all D1 comma D2. When you add these two, you can get D1 comma D2 0 0 such that D1 comma D2 belongs to R. This is an example of a span of a set of vectors, a set of two vectors in R4. Okay, so this set represents the span of S. Now we have a theorem, theorem 4. The span of a set of vectors S equal to v1, v2, etc. vn in a vector space V is a subspace of V. Okay. Now we will prove S is a subspace. To prove S is a subspace, we use any alpha comma beta belongs to F and U comma V belongs to S such that if you assume this, you can get to symbolize alpha times U plus beta times V belongs to S. So this is the required condition for proving S is a subspace. So we start with U is equal to since U is an element of S and S is a span of S is an element of U is an element of span of S, then we can write it as we write this is span of S rather than S. Here we have span of S. We need to prove that the span of S is the subspace, so we write this is span S. Okay, so U and V are elements of. We need to prove that the span of S. Here we have span of S. This is the definition. So we assume U and V are elements of span of S, and span of S takes the form span of S consisting of set of all D1 V1 plus etc. Dn Vn such that Di belongs to this corresponding F. Now we consider U is an element of span S, then U is a linear combination of V1, V2, etc. So I'll write it as D1 times this V1 plus etc. Dn times Vn. And similarly, we assumed that this V is also an element of span of S, then that takes a form. That is again a linear combination of V1, V2, etc. Vn. So we can choose C1, C2, etc. such that C1, V1 plus etc. Cn, Vn. So these are two arbitrary elements of this S. We need to prove that alpha times U plus beta times V is also an element of span of S. So we will evaluate alpha U plus beta V. What is alpha U? That is alpha times U is D1 V1 plus etc. dnvn plus beta times v is c1 v1 plus etc cnvn. Okay, now you can use the distributive property, so that is that can be written as alpha d1 v1 plus etc alpha dn vn plus similarly distribute beta over this addition, so beta times c1 v1 plus etc beta times cn vn, and add all this. Okay, so that is alpha times d1 plus beta times c1 is the c1 times v1 plus etc alpha times dn plus beta times cn times vn. Okay, so this is again a linear combination. Since this is an element of, we can put these values as some e1 e2 etc. So this is e1 times v1 plus etc en times vn. Obviously this is an element of span of S. So this shows that we have already discussed a couple of characterization of subspaces. So this is one among them. Alpha u plus beta v belongs to span of S implies span of S is a subspace. Okay, this proves theorem 4. In this section there is one more theorem. This is the last theorem of this section. Theorem 5. If S is a set consisting of v1 v2 etc vn of vectors in a vector space V, and W is a subspace of V that contains all these vectors. Okay, S is just a subset and W is a subspace containing all these vectors. That means this W contains all the vectors of S. Then W contains all the vectors in span of S. Okay, so we need to prove that whenever we consider a set and a subspace W, this W consisting of each Vi belongs to this W for all I. Okay, so as a consequence we can prove that all I belongs to, or all I is equal to 1 2 etc, and we need to prove that this W contains its linear combination. Okay, dnvn belongs to W for all di. That means once you consider a subspace containing some vectors, then that subspace containing all the linear combinations of those vectors. Okay, or the W contains the span of S. Okay, so we will prove this by proving this statement. This is need to prove. So we start with Vi belongs to W, and W is a, and we have W is a subspace, then this implies di Vi belongs to W for all I is equal to 1 2 3 etc, and since W is a subspace, that implies d1 v1 plus d2 v2 plus etc dn vn belongs to W. Since W is a subspace, it contains all the sum of all the elements of that W. So this is using the scalar multiplication. W is closed under scalar multiplication. So when you multiply with Vi with any di, you can get that's an element of W, and this is using vector addition. This is the vector addition, the closure property of vector addition. So we can say that this implies span S is a subset of W. Okay, that is because if you consider any arbitrary element of the span that takes this form, that is always in W. Therefore, span of S is contained in W. That means W contains all the vectors in the span of S. So this completes this session. The next lecture we will discuss the other sessions dealing with the linear combination. So using this linear combination, we will define a new concept, linear independence in a vector space.